Bismillah ar-Rahman ar-Rahim. Corona effect. And in the last lecture, we have studied the that what is the corona effect, what are the corona discharge, how it appears, and uh, how the ionization of the air occurs around the conductor, and how sound is produced, hissing sound is produced around the corona, and why the violet glow is appearing around the conductor, and what are the audible corona and visual corona, what is the chemical effect of producing the ozone gas, and how it reduces the efficiency. So then we have studied that audible corona are actually the hissing noise heard due to the power loss, and then the violet glow, which is actually the visual corona. We have already studied that the 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 deceptive critical voltage required for the visual corona is greater than that of the audible corona. Okay, so then we have studied the factors affecting the corona, the mechanism of the corona, the advantages and the disadvantages. Now we will study the methods of reducing the corona. So the corona loss can be reduced by using conductors with large diameters. The voltage at which the corona occurs can be increased by increasing the size of the conductor, and hence the corona loss can be reduced. The second method used for reducing the corona effect is the hollow conductor. These are used to increase the effective diameter of the conductor without using any additional material. Since corona loss is inversely proportional to the diameter of the conductor, corona loss decreases with an increase in the diameter. So this is a good effect. This is the good mechanism method used for reducing the corona, and it is also economical, because if you use the hollow conductor, so the inner material which is not actually being used by the current flow, so it will be saved. Okay, and the another method which is very common and can be commonly seen, usually seen in the transmission line, that are the bundle conductors. So these are made up of two or more subconductors and is used as a single phase conductor. Okay, so a spacer is actually uh, installed in between these bundle conductors. These bundle conductors may be two, maybe three, maybe four. Okay, so okay, this is actually the sketch of the bundle conductors with four conductors in a bundle, and all these four conductors actually represent a single phase. Okay, so for three phase system, we need to have 12 conductors, 4 plus 4 plus 4. Okay, now coming to the numerical side of the corona effect. So the disruptive critical voltage is actually the minimum voltage at which ionization takes place. This is called the critical disruptive voltage, and its formula is V D naught. VD is actually the critical disruptive voltage and not represent the audible. Okay, so for this is actually the formula for the audible corona, and we will have a different formula for the visual corona. So first of all, for the audible corona, Vd naught is equal to G naught. G naught is G naught M naught sigma R ln D over R. Okay. So now what is G naught, M naught, and all these parameters? So G naught is the dielectric strength of air. Okay. This is the RMS value. So the RMS value for the dielectric strength of air is 21.1 kV per centimeter. This is constant. Okay, m naught is the irregularity factor, the surface irregularity factor of the conductor. Okay, if the surface is smooth, so m naught will be equal to 1, and the chances of the corona will be less. And if the irregularity and the roughness of this surface increases, means sharp edges occur in the conductor surface, so the m naught value will be reducing accordingly, and the chances of corona will be high, okay, by reducing the m naught value, because this is inversely proportional. So if m naught is less, so v naught will be less, and v naught will be less means the minimum voltage is less, so the corona will occur mm, quickly. Okay, so sigma is the air density factor. It is related to the environmental effect. R is the radius of the conductor. Okay, d is not the diameter. Don't confuse this d with the diameter. D is, here d represent the spacing between the two consecutive conductor. So for example, if we have uh, this is one conductor, this is two, this is three, so this the distance between these two will be d1, and the distance between these two will be d2, and the distance between these two will be d3. Okay, so if this is 5, so this also 5, so this will be equal to 10. 5 plus 5 plus 10. So now we have to find the net d by geometrical mean method. Okay, so 5 into 5 into 10 cube root. Okay, this will be actually the net spacing for all these conductors. Okay, so okay, so and sigma is can be found by 3.92 bp. Here is the pressure, atmospheric pressure. Okay, it is the temperature. Okay, so here the degree celsius value will be put, so it will be converted to kelvin by adding it with the 273. Okay, now let's have a numerical based on the previous formula we have studied. Okay, we have three phase conductor, and each of radius 1 centimeter, spaced at the corner of equilateral triangle. Okay, now the triangle has been arranged in triangular fashion. Okay, equilateral triangular fashion. Okay, so the distance is 250 centimeter. 250, 250, same 250 and 250. Okay, if the dielectric strength of the air is 30 kV per centimeter, this is the peak value, or you can say that maximum value. So for the previous formula we have to convert it into the RMS value. So 30 divided by under root 2. By this way it will be converted to the RMS. Okay, because the formula, the relation between the maximum and RMS is RMS is equal to peak value over square root 2. Okay, determine the disruptive critical voltage at which the corona will occur, and sigma value is 0.96, and the irregularity factor m naught is equal to 0.94. Okay, so now the radius of the conductor is this, d is in centimeter. If this is centimeter, this is given in meter, so we have to convert it in centimeter, so that we have the unanimous parameters. Okay, uh, dielectric strength in RMS. Okay, irregularity factor 0.94, sigma 0.96. This is given. If it is not given, so then we will use the formula we have studied in the previous slide. So V naught is equal to G naught sigma m naught this. Okay, putting the value straight away, so we will get this for the single or the phase value. Okay, uh, for phase to neutral means the phase value Vp, and for VL line value we have to multiply it with the under root 3. So line value will be 183.0 kV. Very simple, just we have put it the values in this formula. Okay, now the visual critical voltage. So I have already told you that the visual critical voltage, the disruptive critical voltage for the visual corona is greater than that of the audible. Okay, and it is actually higher than the audible corona by this term, 1 plus 0.3 divided by square root sigma into r. Okay, the rest of the variables are the same as that of the audible. So we can say that Vv is equal to 1 plus 0.3 divided by square root sigma r. Okay, this is the additional uh, term used for the Vv into V naught. Okay, so if we have the V naught value, so just multiply this V naught with this additional term of Vv. Okay, so this term is in multiplication with this Vv, and this is greater, that would be definitely greater than 1 because 1 has been added to this term. So if this is less than 1, then in that case it will also be greater than 1, because for example if this is 0.7, so the whole term will be 1.7. So in that case too, we have the value greater than the 1. So when we multiply it with V naught means the audible corona, uh, so we will have the greater value for the Vv than the V naught because of this term. Okay, so now let's have a look. Okay, M, mostly the MV means the M was the M was the surface irregularity factor. Okay, so surface irregularity factor for the MV is in the range of 0.82. Okay, for the smooth conductor it is ranging between 0.93 to 0.98. Okay, it may be ideally equal to unity. Okay, for standard conductor it is 0.72 practically. Okay, so now this is the numerical based on the visual corona. Okay, based on the visual corona. So determine the disruptive critical voltage and the visual critical voltage. Okay, means the audible and the visual. For the local and the general corona on a three-phase overhead transmission line consisting of three stranded copper conductors spaced 2.5 meter, the value is given in meter. Okay, so if the rest are of the values are given in centimeter, so we have to convert it into centimeter as well. Okay, and the conductors are arranged in equilateral triangle fashion, means this. Okay, all the sides equilateral triangle means all the sides has the same length. Okay, air temperature and the pressure are 21 degrees C and 73.5 cm Hg respectively. Now in this case the sigma is not given, and rather we are given the temperature and the pressure. B, conductor diameter is 1.8 centimeter. Okay, now the diameter is given, we have to convert it into the radius. Okay, r is equal to d divided by 2. Okay, irregularity factor is 0.85. Okay, surface factor mv. Okay, this is for the audible corona, that is why represented with by m naught. and for the visual corona represented by the MV. Okay, so for in order to find the visual corona, we have to put MV. For the audible corona, we have to put M naught. It has no unitless quantity. Okay, for local and general corona, respectively. Okay, so breakdown strength of the air is this in RMS, kV per centimeter. Okay, so now the solution D is equal to 250 centimeter. Okay, using the same formula of DMD. Okay, so 250 into 250 into 250. Okay, cube root cube root. Okay, so 250 cube into 1 over 3. So cube will be cancelled. So we have used the same formula. Okay, but for the equilateral triangle, the D will be same throughout. Okay, this is equal to the space between any two conductor. Okay, so that is why it is 250. Diameter of the conductor is 1.8. Okay, by this formula. R is okay, D is this, so R will be this by this formula. Okay, temperature is 21. B means pressure, P at 73 mmHg. cmHg. Okay, cmHg. So now putting the formula, putting these values in this formula, disruptive critical voltage. Okay, to neutral means the phase value. So G naught, M naught, sigma R, ln of D by R. Rest of the values are ready, but this sigma is not ready. So we have to find this sigma. Okay, so sigma is here. Sigma is equal to 3.92 B divided by 273 plus T. So 3.92 into B, 73.5. Okay, given B pressure, atmospheric pressure over T21. Okay, 21 degree C from here. So V naught will be equal to 89 kV per phase. Okay, now visual corona. Okay, so for the visual corona, we have the different formula. We have the additional term of 1 plus 0.3 over square root sigma into R. Okay, so in my opinion, there is no need to put these values again. Just put the uh, 89, the previous value of V naught 89 kV. Okay, and multiply it with this term 1 plus 0.3 over this. Okay, so the answer will be 96.71. Look, the VV is greater than V naught for the same environmental condition and same conditions. Okay, V naught is 89, means the chances of here is higher as compared to this. So first you will listen to the audible hissing noise, and then if the voltage, the line voltage exceeds the 96.7 kV, so then with the hissing noise you will also observe the violet glow which will surrounded the conductor. Okay, so for line to line voltage, you have to multiply this with the under root 3. So 96.71 into under root 3. Okay, so this is for the general corona because the value for MV is different for the general. Okay, for the local MV, for the local we have MV value is 0.7, and for the general we have the 0.8. So because of this MV value, different values, we have the different VV values. Okay, VV for the local with zero point 0.7 MV is this, and VV journal corona for MV zero point 0.8 will be this. Okay, so greater is the M value, greater will be the VV value. Okay, means smooth, there is smoothness is high. Okay, as compared to this means this MV is rougher than, in rough condition than this. Okay, so VV is line voltage for the journal corona is 130.16 kV per kV. Okay, for line to line means line value. Okay. In the next lecture we will study the will find out the power loss due to the corona. Okay, the value for the power loss due to the corona. Okay, up till now we have studied that there is a loss, there is a power loss, but what is actually the value in watts for the power loss due to corona? So we will study it in the next class. Okay, so thank you for the moment.